Hi everyone, I'm J.K. Lee from HP Labs. I'm here to present our work CloudMirror, which is enabling technology for bandwidth guarantee in the cloud. So this is a joint work between HP Labs, University of Edinburgh, and HP Enterprise Services. Some of my colleagues from HP Labs are sitting here and can participate in Q&A. So the cloud providers, they want their customers to migrate various applications to the cloud, including some of the recent big data applications like Hadoop. And they require very high network bandwidth. For example, the Hadoop store operation can require something like 500 megabit per second bandwidth for bottleneck-free operation. On the other hand, the user-facing web services, they have very stringent latency requirements. For example, Amazon reported that every 100 millisecond latency can cost up to 1% in their e-commerce sales. And here we have our testbed results showing that insufficient bandwidth can lead to a sharp increase in the response time, web response time. So we ran the Wikipedia benchmark on our testbed and observed that the web response time can goes up to some unacceptable range when the available bandwidth is not adequate to handle the user load. So they confirmed the fact that we need network bandwidth guarantee for predictable performance of various applications in the cloud. However, the cloud providers today, they do not guarantee, do not have such a rich bandwidth guarantee model. For example, Amazon EC2 has some weak network SLA concept like moderate or high bandwidth for different type of virtual machines. And this is the same with other public cloud providers like Rackspace, Azure, and HP Cloud. Then why don't we have such good network bandwidth guarantee in current clouds? First, we need a good network abstraction model for the tenants to specify their bandwidth demands. And the challenge here is that the application components, they typically show very complex communication patterns. Here we see that communication patterns observed from the Microsoft Bing.com data center. In here, each node represents a component of multiple virtual machines. And the communication between the components show very different patterns like linear, mesh, and star topology. And mapping this complex communication structure onto the typically tree-shaped and homogeneous data center physical topology is not straightforward and is a challenging problem. So to tackle this problem, we propose a solution like a CloudMirror, which is composed of two parts. So we first provide a model, new network abstraction model, so that the tenant can select the bandwidth demands. And we have an algorithm that takes the model as an input to place the virtual machines and do admission control to ensure the model is achievable in the physical infrastructure. Of course, we need some runtime mechanism to enforce the guarantee in the physical infrastructure, and we rely on some previous work and ongoing work, and definitely the previous talk of NICPIC and vShaper are very relevant technologies to enable this bandwidth enforcement in the physical infrastructure, so we can leverage that. So our solution for the new abstraction model is called as Tenant Application Graph, or TAG. And compared to the previous approaches like pipe model, virtual cluster, or VOC, TAG provides very good flexibility and efficiency and is easier to use. And we also have a new virtual machine placement algorithm that efficiently utilizes various computer and network resources in the data center by intelligently leveraging the new TAG model. So together, the TAG model and the placement algorithm can achieve something like 2x bandwidth efficiency, as we will show later, with marginal algorithm complexity. So before going into the CloudMirror, let's go through some of the prior work and their shortcomings quickly. The first one is pipe model, which has been known in the community for decades. It specifies each and every VM to VM communication. So it's very tedious to use because the users have to specify a large number of pipes. For example, n square number of pipes when n is the number of virtual machines. and its algorithm complexity can goes up to something like n to the power of 4, so it can take a long time to compute the optimal placement of the virtual machines. And the Popa model also lacks statistical multiplexing. So typically load balancers today, they do not do very perfect uniform distribution of the load to every destination. And then the users cannot update their pipe model every second or every minute. So they typically end up reserving some kind of worst case bandwidth of the peak load for each pipe. And we have an example, there is a benchmark report from on Amazon Elastic Load Balancer, which shows that the sum of the peak loads on each pipe, toward each destination, can be as large as twice of the peak aggregate load. So the use of pipe model in this case can lead to 2x overprovisioning of the bandwidth. So another model is virtual cluster, also known as a hose model. Here, the virtual machines of the entire tenant is forming one virtual cluster, and each virtual machine is connected to the virtual switch through a hose which specifies the bandwidth guarantee for that virtual machine. Because it uses the per VM bandwidth specification, it can take the advantage of the statistical multiplexing, and it's easy to map on the physical topology because this model resembles the behavior of a physical switch. However, this model hammers down the various application communication patterns onto this homogeneous switch model, so it can lead to inefficient bandwidth reservations. So we have an example of standard 3-tier web application composed of web tier, application tier, and database tier. Very simplified example. And also for simplicity, let's assume that the same n number of virtual machines on each tier, and we have the same per VM network bandwidth guarantee B for the communicating tiers. And the database virtual machines can talk to each other, so we also have a self-edge representing the intra-tier communication. And here we have the virtual cluster modeling of this example. The web virtual machines have a B amount of guarantee toward that virtual switch, and then application virtual machines have 2B amount of guarantee, B toward the web tier, another B toward the database tier. And the database virtual machines similarly have 2B amount of guarantee, a B toward the application, another B for intra-tier communication. And in this physical deployment example, let's assume that web and application virtual machines are placed under the same server, and the database VMs are deployed on another server. And the links connecting the two servers to the top of rack switch needs to reserve 2BN amount of bandwidth to implement the virtual cluster model. However, the actual demand that needs to be reserved on those physical links are just BN, because only up to database traffic traverses that physical links. So here, the virtual cluster model can lead to 2x bandwidth uses compared to actual need. And there is another advanced model called virtual oversubscribed cluster from Microsoft. And it's a 2-level hierarchical switch virtual cluster model in which each application component can map to one virtual cluster, and all the virtual clusters are connected to the root virtual switch through oversubscribed links to accommodate the communication between different virtual clusters. This model is also easy to map on the physical topology because it looks like a tree, but it doesn't also exactly capture the generic and general application structure, so it can lead to inefficient and inflexible mapping. We show that in our paper through the example walkthrough, and we will also compare this model against ours in the evaluation section. So, so basically, the reason why the previous model have not been so much efficient or flexible is that because they try to give a tenant of abstraction of the physical topology on top of which the applications, tenants can deploy their own applications. However, there is still a significant amount of work left to be done by the tenant and users to convert their complex application structure onto these homogeneous physical network models. In addition, those physical network models are typically rigid or homogeneous, so it can be very inefficient and inflexible in capturing the actual application needs. So for this reason, we believe that the network abstraction exposed to the tenant should model the network's application rather than the physical network. So we propose the tag model, which aims to closely mirror the application needs. Yep, I missed the missions. So our solution tag is a graph, and each vertex in the graph represents an application component. And here the component is defined as a set of virtual machines that perform the same function. And in the platform as a service case, you can see this as a set of Java virtual machines. And the pair of communicating tiers here are connected through directional edge, which represents the per VM sending bandwidth guarantee and receiving bandwidth guarantee. So in this example, each web virtual machine is guaranteed bandwidth B1 to send traffic to any set of virtual machines in the database tier. At the same time, each database virtual machine is guaranteed to receive B2 amount of traffic from any set of web virtual machines. Here we have an alternative illustration of this tag model. So for example, the directional edge that connecting two communication tiers can be represented as a virtual trunk. Here the web virtual machines, each web virtual machine is connected to the virtual trunk via a dedicated link, the directional link with a B1 amount of bandwidth guarantee. At the same time, the virtual trunk is also connected to each database virtual machine with a dedicated directional link with B2 guarantee. So we believe this virtual trunk is a new concept, and the total amount of guarantee that this virtual trunk provides can be computed as the minimum of N1 B1 and N2 B2. This is because that the total amount of sending rate from the web tier cannot exceed the total amount of receiving traffic, receiving rate at the database tier, and vice versa. And the self edge to describe the intra-tier communication for the database tier can be represented as the virtual switch as we discussed before. So the benefits of tag includes that tag is intuitive and descriptive. So it's easy to use because it directly mirrors the application structure, unlike some previous model that tried to capture the network physical topology. And at the same time, the tag users, they don't need to be concerned with the network topology, unlike the previous models. For example, VOC requires the user to specify the oversubscription ratio of their virtual network topology. And tag is efficient because it directly captures the application demand. Here we have the same three-tier application example we showed before. And for the same physical deployment example, web app in the same server and the database in another server, the amount of bandwidth we need to reserve on the physical links is exactly Bn, as represented by our model. And we also mathematically proved that the tag model requires less or equal amount of bandwidth compared to VOC. And tag is supporting directional edge, and so that we can naturally accommodate the middle boxes, because middle boxes often impact only one direction of the flow, and the query traffic typically consume less amount of bandwidth compared to the response traffic. And in addition, tag is using the per VM bandwidth specification so that it can take advantage of the statistical multiplexing, and it can be flexible to time-varying load balancing. In addition, the per VM bandwidth numbers don't need to be changed while the tenant size increasing or decreasing because of the auto-scaling or flexing. In this example, we have the tag with web tier and database tier, and when the tier size increases by 10x, the tag numbers do not change at all. On the other hand, all the pipe reservations need to be updated. And here we have some supporting example from Netflix, which shows their varying the network read and write numbers per node per virtual machine network demand does not change while the tier size increases from 48 nodes to 288. It was measured from their Cassandra cluster running on the Amazon EC2. So this confirms that the network per VM network bandwidth is quite relatively stable and flat while scaling happens. So far, we looked at the tag model as a network application abstraction model. And now let's move on to the virtual machine placement algorithm. So our algorithm takes 3 inputs: the tag input as a description of the new tenant we want to deploy. And we take the available virtual machine slots. And also, the algorithm takes the network topology and the amount of bandwidth reserved on the physical links for the existing tenants as an input. And the algorithm computes the optimal VM placement and also the amount of bandwidth we need to reserve for the new tenant. So please remember that we pushed up our tag abstraction model close to the application. So the goal of VM placement algorithm is to fill up the gap between the application model and then typically tree-shaped physical topology. So while we do that, we want to deploy as many tenants as possible while guaranteeing the network SLAs specified in the tag model. We achieve that goal by doing maximizing the consolidations. So first step is to localize the traffic, and by doing that, we want to save core bandwidth, which is deemed as a bottleneck in the tree-shaped topology. The first step is to identify the smallest feasible subtree that we can deploy the entire tenant. Is similar to the octopus. So in this simplified example, we have a tenant with 4 virtual machines, and we know for sure that this tenant cannot be placed under the same server because the server has only 2 virtual machine slots. So we decided to place it on the Tor switch. The next step is to identify the tiers that talk to each other and place the heavy talkers under the same server or same subtree. This can be achieved by solving some similar to the size min-cut problem. And for the remaining tiers and virtual machines, we try to fully utilize network and compute resources, for example, by placing the high bandwidth and low bandwidth virtual machines together under the same server, even though they don't talk to each other. So this can be done by solving something similar to knapsack problem. So one thing to note here is that the size min-cut and then the knapsack problems, they are all already been heavily used by the algorithms for pipe models. The major difference is that the algorithm complexity of our algorithm, for example, the size min-cut is a function of the number of tiers, not the number of virtual machines. So that's how we save the algorithm complexity. So in order to evaluate the performance and efficiency of CloudMirror, we simulated the bandwidth reservation and virtual machine placement given a stream of tenant arrivals. As for the tenant workload, we used the Microsoft Bing.com data, and which contains the various communication patterns and then various size of components. So we take the tenant as a set of connected components in the entire connected graph. And we thankful the authors for kindly sharing data for us for this simulation. And for the topology, we simulated 3-level tree topology modeling after the real HP data center, which has around 2,000 hosts and then 50 virtual machines per host. So here on the left side, we compare the total bandwidth reserved throughout the network for the tag model against the virtual cluster and VOC. For the tag model, we used our CloudMirror VM placement algorithm, and for the virtual cluster and VOC, we used the octopus algorithm. For fair comparison, we simply assume that the network is never a bottleneck, so we simply ignore the link capacity constraints when placing virtual machines, so that all the models can deploy the same set of tenants. here we see something like 76% more bandwidth required by the virtual cluster against the tag model. And we have seen up to 2x or more difference between tag and virtual cluster from different kind of workloads. On the right-hand side, we consider the link capacity constraints, and we evaluate the impact of different network capacities on the virtual machine slot cluster utilizations. So we control the network capacity by changing the physical network oversubscription ratio in the simulation. And we deploy the tenants one by one and plot the utilization of the data center VM slots achieved when the first tenant rejection happens due to some resource constraints like network or virtual machine slot. We clearly see here that the CloudMirror can outperform VOC in terms of VM slot utilizations. Okay, to conclude, our contributions include the tag model, which models application structure instead of physical data center topology. And our model is graph-based, and it's easier to use and more efficient and flexible compared to the prior work. And the placement algorithm we propose can efficiently map the tag model onto the tree-shaped topology. So as a future work, we are planning to prototype the CloudMirror system on OpenStack with the elastic switch as a mean to enforce the guarantee in the infrastructure. And we want to have a good pricing model for tag to benefit both users and operators. And we plan to extend our algorithm to consider other constraints like high availability and reliability. Thank you. I'm ready for questions. And one more note is that HP Labs is hiring and good networking and systems researchers. So please contact me and or other folks from HP Labs if you are interested. Thank you.
Hi, I'm Ishai from Microsoft Research. So you were using my data, actually. So.
Thank you very much.
So a quick question about, I think you referred to the point of like the context of like what happens if you have varying traffic, varying demands, bandwidth demands across time, let's say differences between day and night. How do you accommodate this in your framework, in your algorithmic framework?
Thank you for asking the questions because I prepared 2 more slides in the backup. So this is a very challenging problem. And first, I believe that the per VM bandwidth number we need to set in our tag model is a function of 2 things. One is the processing capacity of the virtual machine and the workload. And the processing capacity can be easily kind of profiled, so let's ignore for that for now. And the workload, of course, changes as we pointed out. And I believe that the large shift in the application demand should be handled by auto-scaling or flexing, by deploying more number of VMs or reducing the number of VMs. And then we have shown that our tag model can be very flexible while the scaling happens. And also we show that from the Netflix data that typically the per VM bandwidth demand does not really change while the scaling happens. And when then when the size of the tier or size of the tenant is fixed and we don't change it, and because of some constraints or because we don't need to, but still there is a time variation. And the one simple way to handle this case would be maybe just reserve for the maximum, considering the maximum capacity of the virtual machine for processing power. But if you want to do more optimization, there are 2 options we can consider. First one is measure and profile the time-varying bandwidth. And actually, it's done by the Purdue researchers and presented in the SICOM last year. It probably was there. And it probably works for something like the big data batch processing because the time-varying network bandwidth demand is kind of repeated. And you can profile it. For the same Hadoop sort operation, you know when the peak bandwidth is needed and when the bandwidth demand is very low. So then once we know profile, we know the pattern, then you can actually schedule the different jobs to avoid the collapse of overlap of the peaks from the 2 different jobs. So that can be done. Another thing that I want to show here is that it's not a very complete result, but we ran when we ran this Wikipedia benchmark on our testbed, we observed that the network bandwidth demand is really proportional to the number of user transactions. So this is the simplified topology of the Wikibench. So we have 4 components: client, web app, and database, and cache. And so basically we have 6 directed edges. And the network bandwidth demand for each edge normalized by the number of transactions are relatively flat. Although each link show the really time-varying bandwidth over 24 hours time span, but when we normalize it, it's really flat. So we kind of hope that once we can have some good trend of profile or estimation of the user transactions and user requests, we can hopefully compute the demand in the intra-data center communication easily based on the trend. That's kind of my long answer.
Okay.
Does it make sense?
Yeah, thanks.
Thank you.